In this video, I'll introduce the central limit theorem. In your textbook, on page 290, in section 4.11, it talks about the central limit theorem, and the first paragraph in this section is so good that it is worth just reading. And this is really all I want you to know about the central limit theorem for this class. So it says, the central limit theorem is by far the most important result in statistics. Many commonly used statistical methods rely on this theorem for their validity. The central limit theorem says that if we draw a large enough sample from a population, then the distribution of the sample mean is approximately normal, no matter what the population the sample was drawn from. This allows us to compute probabilities for sample means using the z-table, even though the population from which the sample was drawn is not normal. All right, so let's make it more precise. A bunch of data points, x1, x2, all the way up to xn, and they're independent and identically distributed observations from some population. It doesn't matter what kind of population. It just needs to have a mean mu and a standard deviation of sigma squared. So mean and standard deviation must exist and be finite, which, by the way, is not always the case. Normal sample mean that we've observed before. So this is a function of a bunch of random variables. So here we're thinking about the sample mean as being a random variable. Then what the statement of the theorem says is that once you get enough data, once n is large enough, you have enough observations, the sample mean becomes itself as a statistic, as a random variable, is distributed as normal with mean mu and variance sigma squared over n. So the sample mean approaches the true mean, at least approximately. So if you want to get more precise about these, this is what subsequent courses in statistics will talk about, what this really means in a technical sense. But for us, we just take it as the fact. So this also implies that the sum of all these xi's is distributed as normal with mean n times mu and variance n times sigma squared. Approximately, anyway. Again, approximately. So you might naturally ask, what does large enough mean? How many observations do we need it to be enough? And typically, once you have n equals 30, the central limit theorem, or CLT, central limit theorem, is a good approximation. Here's an example from your book. This is 4.71 on page 293. So it says, at a particular university, the mean student age is 22.3 years, and the standard deviation is 4 years. You randomly sample 64 students from the entire student body population. And then ask, what's the probability that the average age in this sample is greater than 23 years? So here's how you solve this. You got to take the word problem and figure out what the symbols are. So mu here is 22.3. Sigma is equal to 4. The number of samples that you're observing, the number of observations, is n is equal to 64. N equals 64. And it's asking, find the probability that the average age is greater than 23. So x bar is average age in the sample of size 64. We want the probability that x bar is greater than 23. The central limit theorem says that x bar is distributed approximately as normal mu, which is 22.3, and then with variance sigma squared, so 4 squared over n over 64. Right? And 4 squared over 64, that's equal to 4 over 8 squared, which equals 1/2 squared. Okay. So now we can use the z-table, or if we want to plug it into R, somehow find the probability . So this you can write out as the probability that x bar is greater than 23 is equal to 1 minus the probability that x bar is less than 23. Then you can use the cumulative distribution function for a normal random variable with mean 22.3 and standard deviation 0.5. So this is the R code to solve this. So when you plug this into R, you get 0.0808 is your answer. Okay, so the point of this example is, or the power is, that we knew nothing about the distribution of the ages of the students. All we know is that there is some mean age and some standard deviation. In reality, there's a finite number of students, so there's 20,000 students or whatever at this university. And even though we don't know the true mean, we can say things about this sample mean without knowing the whole distribution. So it's a powerful tool for summarizing.